Hello students, in the first YouTube video, we have seen some salient features are the characteristics of the curve tracing part 1, which is unit number 4, and now we'll continue that and we'll understand the next points of the curve tracing. So in the last example, we'll see that x cube minus y cube is equal to 3axy. Here the curve is symmetric through the line y is equal to minus x. That is, you are given x cube minus y cube is equal to minus a 3a xy, and the curve is symmetric to y is equal to minus x. Then we'll go to the next point, that is the region or extent where the curve is either present or absent, and then we have to find the trace of that curve. So the next point is region or extent. Region or extent is obtained by solving y in terms of x or x in terms of y. Real horizontal extent is defined by values of x for which y is defined. Real vertical extent is defined by values of y for which x is defined. The region of absence or imaginary region is the region in which the curve does not exist. In such a region, y becomes imaginary, that is undefined for values of x or vice versa. That is what we call the region of presence or absence. Then we'll see the next point, asymptote. An asymptote of a curve is a line which is tangent to the curve at a point at infinity. That means this is an asymptote to the curve. This tangent meets the curve at infinity. That means it does not touches the curve at all. This is called an asymptote. Then parallel to x-axis are obtained by equating to 0 the coefficient of the highest powers of x in the given equation of the curve. That is, asymptote parallel to x-axis are obtained by equating to 0 the coefficients of the highest power of x in the given equation of the curve. Parallel to y-axis, that is the asymptote parallel to y-axis, are obtained by equating to 0 the coefficient of highest powers of y in the given equation of the curve. For example, x square y minus x is equal to 0 is of third degree. Now the degree of this is 3, therefore it has maximum 3 number of asymptotes. Y is the coefficient of highest power of x, that is of x square. The coefficient of this x square is this y. Thus asymptote parallel to x-axis is obtained by equating to 0 the coefficient of highest power of x, that is y is equal to 0, and x square minus 1 is the coefficient of the highest power of y. That is, if you take the y common from x square y minus y, then y becomes outside, then x square minus 1 becomes the coefficient of the highest power of y. That is, now equating this to 0, we get an asymptote parallel to y-axis. X square minus 1 is equal to 0, or x is equal to plus or minus 1 are two asymptotes parallel to y-axis. Then we'll see what is the origin. The next point for considering the curve tracing is the origin. If origin, that is 0, 0, lies on the given curve, then there will be no constant term in the equation of the curve. Now, to find the tangents to the curve at the origin, when the curve passes through the origin, then the tangents to the curve at this origin are obtained by equating to 0 the group or collection of lowest degree terms in the given equation. For example, here you are having y square is equal to 4x. Now, y square is equal to 4x is an equation of a parabola, and that parabola we have seen is symmetric to x-axis, and at x is equal to 0, y is also equal to 0. So therefore, 0 lies on the curve. The lowest degree term in this is 4ax. Lowest degree term is 4ax equated to 0. That means you are equating 4ax is equal to 0. That implies x is equal to 0, which is y-axis. X is equal to 0 is the y-axis as the tangent to the curve at the origin. That means y-axis becomes tangent to the curve at the origin. Then if we consider x cube plus y cube is equal to 3axy, we have seen that this equation is symmetric through the straight line y is equal to x, and the lowest degree in this is the term 3axy is equal to 0, which gives x is equal to 0 or y is equal to 0, which are the two tangents at the origin. So that means x is equal to 0 is y-axis, y is equal to 0 is x-axis. Therefore, at this origin, you get two tangents to the curve. Example, third, a square y square is equal to a square x square minus x raised to 4. Lowest degree term is, again if you take this on this side, you get that y square minus x square equating to 0 gives y is equal to plus or minus x as two tangents to the curve at the origin. Then we'll see the next point, that is what we call the multiple point or the singular point. A point through which r branches of a curve pass is called a multiple point of the rth order and has r tangents. Thus, at a double tangent, a double point, two branches of the curve pass. Double point is classified as a node, a cusp, or an isolated or conjugate point according as the two tangents are real distinct. So if the two tangents at the origin are real and distinct, that point becomes a node. The two tangents are coincident, that means both of them are same, then it becomes a cusp. And imaginary, that means the tangents are imaginary, then it becomes an isolated point or a conjugate point. Multiple points are obtained by solving for f of xy e the three equations, that is f of x xy equal to 0, f of y xy equal to 0, and fxy is equal to 0. So this is a partial derivative of f of xy with respect to x, and this is a partial derivative of f of xy with respect to y. Then by solving these three equations, we get the multiple points. Then the next point is intercepts. The x-intercept, that is the point where the curve meets the x-axis, is obtained by putting y is equal to 0 in the given equation of the curve and solving for x. Similarly, y-intercept, where the curve crosses the y-axis, is obtained by putting x is equal to 0 in the given equation of the curve and then solving for y. Then points of intersection. When the curve is symmetric about the line, y is equal to plus or minus x. The points of intersection are obtained by putting y is equal to plus or minus x in the given equation. Now, these are the main points which are to be considered for tracing the curve. Then we will discuss after all these points, by putting these, then we can trace the curve in the Cartesian form. Thank you.